In this tutorial video, I will introduce PCED3, a computer software for poly-crystalline electron diffraction simulation and phase identification. The current version is 3F. This is one of the main components in Landyne software suite for electron diffraction simulation and crystallographic analysis. You may download the software suite, including user manuals, from the website on the screen. We already explained how to download and install the Landyne suite together with the Java runtime environment and the Java Advanced Image System in the first video of the series. You may follow the video to download and install Java and Landyne suite on your PC. I assume you have the software suite already installed in your PC, so you should have this icon in your PC. Double-click this to start the launcher. If you purchased a license, please copy the license file to Landyne 3 folder and Programs subfolder. Let me show you. In my case, this PC, and go to C folder, Landyne 3 Programs, and here are the PCED3, and this is PCED3 license key. Click this icon in the launcher to start the PCED program. A license dialog will pop out in case you don't have a license file. Then you may select the demo mode to continue. Let me briefly introduce the functions on the menu first, and then go to detail with examples later. In the menu, first is crystal. The first one is for you to prepare a new crystal file, and then you can load phase 1, load phase 2. Only 2 phases allow to simulate it at the same time. Exit will leave the program. In experiment, you can load experiment diffraction pattern, show which file name is. You can erase the pattern. A few processing allow you to invert the brightness, and you can adjust the grayscale, and you can resize and rotate the pattern. You can make alignment the pattern to the center. And then this one is for you to do the calibration to adjust the spacing marker. And for the phase identification, you allow to show the diffraction pattern in the half of the screen. Other half will be the simulations. In simulation, we have the theory, kinematic diffraction theory and dynamic diffraction theory to select it. And you're allowed to define the crystal average grain size, the peak profile, texture model, and you can index diffraction ring, and there are a tool for you to change between Miller-Bravais indices. and the Miller indices. And this parameter table is this table here. And you can show all of them or hide all of them. In pattern, we have a region of interest for you to save the area within that your interest, and also the TIFF for TIFF file resolution. The file can be saved in JPEG or TIFF. You also can save diffraction and intensity list, including other options which can be defined in the preference. In table, we provide a element periodic table like this, and also the space group table like this. You can search for the symbol of each space group with a number and symbols. These tables allow you easily to prepare the new crystal face. In option, we have a look and feel. We have 3 choices for the style of the window, and you can hide the toolbar or show the toolbar. So this is hide, show them again. You have reset the color. This is for phase 1 and phase 2 for the diffraction peaks, and also the diffraction ring. In help, you have a current drive and SN serial number. We already introduced how to get a serial number in previous video. It's very simple. You click here and you got this number here. You can take a snapshot of this dialog window and send to us for us to prepare the license file for you. The last one is version, and it tells you which program is, which version is. This one is PCED3F, and which the program updated. The drop-down menu includes all the functions. Graphic menu bar is only selected part of them, which is important, can be used conveniently. The only one exception is the drag and drop box, only available in the menu bar. Now I will show you how to create a new structure file. If you already watched the other Landyne tutorial videos, for example PCED3, and are familiar with how to prepare a new structure file, you may move forward to next topic. Landyne software suite is distributed with a collection of structure files, so you can use PCED3 immediately and show you where the structure files are. In this PC, C folder Landyne 3, and see here structures, and all these structures already made. We are going to use sodium chloride as an example. Click New, and here you can type This is a cubic structure. It's FCC. Lattice parameter is 5.6402 angstrom. B and C equals A. Alpha, beta, gamma equals 90 degrees. The space group is 225. Let's check the symbol. Fm-3m. There are two independent atoms here. Atom 1 is sodium. Atom number is 11. Atom coordinate is 0, 0, 0. Occupancy 1. Add atom on. Second atom is chloride. Number is 17. Coordinate is 0, 0, 5, 0. Occupancy is 1. If you type something wrong here, you want to change something, you can select this item and remove it. It will go back to here. And this one is all correct, so we can add it back. This shows the independent atoms. Number is 2. And here, global isotropic temperature factor, usually we just put a 0. If you put a non-zero number here, high G value diffraction intensity will drop down. Here you write something where you get this file and some particular notes here. Then you click save. We already have this file there. So if I save, it will replace this one. Now I'm going to save here. So this is how you prepare the new file. The format of the structure file is simple. You can open it in any text editor. Let's check out C folder. Landyne 3 structure, sodium chlorate. This is the title, and this is the cell type FCC, F-type. This is lattice parameter. This space group number, symbol, 2 independent atoms, atom coordinates, structure, temperature factor, and notes. In the following, give the explanation. What is the keyword is. Although the structure file looks simple, you may have a problem if you write or edit a file in which it doesn't meet the required format exactly. Therefore, we suggest you use the template to create a new file. In order to avoid any mistakes, you should view the structure with the SVD2 after you created the new structure file. This is the SV82. We already have another video to introduce the function of these programs. The template in SV82 also provide a function for you to convert structure file in other format. For example, CIF, to convert the format to the format we used in Landyne software suite. Let's do the PCED pattern simulation now. We can load the new crystal file from load phase 1 or load phase 2. We also have a default file already here, aluminum default. In the second phase, if we select here, magnesium default, we can show this table. We can enlarge this table. This is parameter tables. We load a new structure files. Those files will be seen in this table. Aluminum default and magnesium default. The simulation allows you to simulate in phase 1 or phase 2 or phase 1 and phase 2 together. All the parameters about the simulation is shown here. File name, the key factor will control the profiles, and the grain size. This is in plane, and this is the height, and the texture defined as out of plane along to 001, and the match factor also control the textures is selected as a 1. We just introduced the structure file and the parameter for simulation. The other parameter are given here in calculation. The high tension is 200 kV. You can change any high tensions that in your max scope. And this G max is set as a 1.0, 1 over angstroms, and this gave you the largest G value in the simulation. Currently we use kinematic diffraction theory, and here are the mass. If you use 2 phase here, start point is 50-50. If I use only 1 phase here, there will be 100. If using the second one, and the other part is 100. Let's try the first with the aluminum. And here we have the Dspacing zoom. Start point is 1.0, and here are the intensity scale 1.0. Simulation is simple. Click calculate. Now we have the aluminum diffraction peaks. This is like in the X-ray powder diffraction case. We can zoom this one. We can increase the, and if I calculate the magnesium, I'll disconnect this one. We can show both phases together. One in red color, one in the blue color. As you remember, in the patterns options, we can reset the peak colors for phase 1 and phase 2 here. Default is blue and red. In two-phase case, we can adjust the mass ratio of this two-phase. And you can see magnesium phase diffraction is reduced. If you move to the other side, aluminum phase mass is and also peak reduced. This one, when we do simulation, we can roughly estimate it. If you have a two-phase case in your sample, the mass ratio is just roughly estimate for this two-phase. Now we leave one phase there, remove this one. We change the Gmax to 1.5 and do the calculation again. And you can see that more diffraction peak come out. We'll go back to 1.0, do it again. You see that cutoff for the high G value peaks. And now we're going to show you the profiles in the simulation. And here is show the peak and profile together. If we show the profile, no peaks, it's showing in the shadow like this. And the profile is, of course, controlled by grain size. We'll show that later. You can select solid or just the curve. So this is the curve, and this is solid, and this is peak only, no profile, so just peak position. Normally we have all of them on with the solid shape. And for teaching, and we also can include the background causing by the incident beam. So the incident beam included now, and this give you some background to the peaks. And you can control, depend on the exposure time and the beam intensities, you can control the beam. This is a long exposure time or a very strong. And you can change the pseudo widget, the functions. I will show you different profiles. In addition to the simulation in kinematic diffraction theory, simulation in dynamic diffraction theory is also adopted in this program. You can select the simulation theory, and here dynamic. Then you have a dynamic diffraction theory. The calculation in kinematic diffraction theory is much faster and accurate enough for phase identification. The simulation in the dynamic theory can use for teaching or some special case in the research work. The background on the theory can be found out in the reference in the user manual. Now we use the default file aluminum to compare these two simulations. First, we get the grain size dialog from here, and here are constant K. We can control the profiles, mostly related the full width at half height, and the diameter is in plane, and let's change it to 100 nanometers, and the thickness is 400 nanometers, and this is for phase 1, and do the calculation. This is for the dynamic diffraction. Now let's look at this phase peak height and select it here, kinematic diffraction carry, and do calculation, and pay attention to this height. Reduced. The other height also changes slightly, and for the simple aluminum phase, it shows slightly different result for the dynamic carry and kinematic carry. Now I explain to how to index the diffraction peaks. Here are the indexed labels. Move this down, and see here are phase 1, and we have phase 1 here. Once we selected the phase 1 index, immediately here show the index for aluminum is 111 peak, 200, 221, 220, 311, and this 222. Here are the diffraction peaks are not many. They could be very near to each other, so we have to have a plan to position of the index label. So in this case, we use the adjustment, and let's show. If I show the guideline, it will show this one is a pole here, so that will be the top point. If I select the top point first and move my mouse to this display area, and I can use the arrow key to click here to control where the top point is. Suppose we selected to this point, and we select another one is baseline, and again click on the display area, then again we use the arrow key, and then we can see the label position are changed due to the top point and the baseline. Adjust this top line and baseline, we can position of our index label to ideal position. So let's see, top point, click in the display area, and I lower the top point, and now the labels are more separate, and I go high, this label were more close to each other, and I can move the top point on the left and right, will control all the labels come to right or left. If I have a two-phase here, and I put the second phase on and do a calculation, so now it's a little complicated. There will be, and I first will think about is making the correct G-space zoom and make the intensity high for both phases. And this is for the first phase, and I can move top point to the center. And since that diffraction from second phase magnesium is more dense, and I used the aluminum as the first line and the magnesium as the second line, so I can reduce the baseline here for aluminum and select the second phase here, and again baseline, click here, and you see the diffraction index for the magnesium is come to the second lines. And again I can control the top line, and now for the second phase here I can make them come together or separated. Of course you don't want to show the guideline to people, so for the second phase and the first phase, and I will select not show the guideline. But still, this, now we got the whole pattern are indexed for two phase. The aluminum phase is in the first line, magnesium phase in the second lines. You have to know that's how to use the adjustment. If you only have one phase, you don't want to show the link lines. And for example, I got only aluminum here. I move the baseline lower, click, too much, show the line. Oh, this top line was too near. I moved top line up, top point up, and now move the baseline, click here. So, but I don't want to show the link line. You can uncheck this. And of course, you have to move the baseline back. So this way you can position your index label. Now I explain how the texture or the preferred orientation affected the diffraction pattern. Let's change it to the G max to 1.2 and calculate. This is in simulation texture model. The texture model we use is March texture model. There are two types. One is out of plane or in plane. In our case, we use the texture 001. For March parameter, 1 means full random, no preferred orientation or texture, and 0 means fully textured. And see, this is for phase 1 and this is phase 1, and watch how the intensity changes if I change this match parameter here after calculation. See this 200 peaks going up and more because of this near full texture 001. So the 200 peak and 001 are the same for the cubic, and when we have a full textured, then we only have the 200 very high, and so totally change the pattern of diffraction. And let's go back and watch the 111 peak going up, and this is total random. 111 peak is the highest peak. Let's look at it for 111 orientation for texture. Calculate. And see, this peak disappeared. And further, 220 going up and further. And finally, for the 111 orientation in extremely case, 11220 are only peak appeared. Let's go back. So the texture is very important. Interpret your diffraction patterns. One thing I also point out for electron diffraction pattern and X-ray powder diffraction pattern, there are different geometries, because for electron diffraction pattern, the incident beam is perpendicular to surface. For powder X-ray diffraction, the incident X-ray beam has angle to the surface. So there are two different geometries. For totally random patterns, you can use the powder X-ray diffraction pattern to index the electron diffraction pattern. There are no difference. But once they have textured, these two experimental results will show a different because of the texture. If you want to hide the simulation result, you can open the profile dialog, which is in simulation profile dialog, and also for the index label is this one here. You turn off the peak and profile, and then turn off the index label. There are two ways to load the experimental diffraction pattern. First one is traditional using Windows file system. You click experiment menu and load the EDP and follow the file system, find out so you get your diffraction pattern loaded. Let's clean out. The second way is first find out where the diffraction pattern is. Then you can drag and drop to the drop box to load it. Hold your mouse left button and drag it. And you see here a move sign show up and release it. You also loaded your diffraction patterns. Two types of diffraction pattern image format can be loaded, both JPEG and TIFF. When you load the TIFF file, you must have the Java Advanced Imaging library installed, which is explained in our first video in the series. You can make several image processing before do the face identification. Image processing in the experiment menu. First, let's do the invert EDP and grayscale. If the EDP is white background, here are the colors on the background. This is already set to 248. If you have it in 255, and here is more bright. If you can see here also more bright, so you can reduce the grayscale to a little bit, so make the extra side matched with your image. Suppose you load the image in black background, and you can also match the side is more clear. Now the edge is white, so you can move the grayscale to make the match. So it looks like one image in the display area. Let's go back to the white background image, and this is 56. Next one is you can resize or rotate the image. Let's do the resize first. The image we loaded, the useful area is a little smaller than the display area. Then you have the extra edge there. And now we increase the image a little bit, maybe to 1.2, and this use the foley of the whole area. And we have a line of entrance line when go to the CCD camera, leave a track here. If we want to move the track on the right side, we can do the rotation. 90 degree, or whatever you want rotate your image, you can do this. After all of this, you need to move your diffraction pattern to the center, the shift and the center EDP. You click here and multiple ring will come out. You can control how many rings appear here. Let me put 5. So there are 5 of them. So your selection of how many. The circles there, and you can show or not show. With reference to the green ring, you hold your mouse left button. You can make a small adjustment. So make the ring perfectly match with the reference ring. And once this done, you close. And this is the pattern are centered. Before face identification, one important operation is to calibrate the Dspacing zoom factor. You may select one of the ring and measure the radius of the ring using the scale bar in the experimental electron diffraction pattern. In my case, this first ring is 0.4277 1/4 extra. Let's go to experiment menu bar, adjust the G value, so is 0.4277 1/4 angstrom. But this marker is not on this ring, so we need to adjust the G zoom. You can click here and use the arrow key. So we got this marker on the first ring. Then I do the update here. Face identification means that you have a experimental electron diffraction ring pattern, and you have a list of possible crystalline phases, and you want to know which crystalline phases is in the experiment by matching the simulating pattern to the experimental one. In our case, we know this pattern is from aluminum. First, let's turn off the marker. I'll show mark here, and we're already simulating the patterns, and we turn off it, not show in the peak and the profile, so we bring them back. And now you see the position and also the intensity scale. The first ring is most intensity one, and second one are here, and so it's a perfect match. So this one is identified as aluminum. We have another way to show the experimental pattern to half. So in this case, you can put the ring tab half or full. If we put a full ring here, you can see the ring position. and the intensity scale there. And you also can put the half ring here, and this quarter area we can put the index label here, so making the whole pattern experiment, simulation, and index. To show the index here. And remember this, the last ring is not show the index. We can turn the guideline here and click here using the key arrow, and we also have the show the link. If I show the base here and lower it a little bit too much. So we have all the diffraction peak indexed. PCED3 allow you to identify two phases in the same time by using composite diffraction pattern from two-phase mixtures. Please remember in simulation to use the texture factor if texture in samples, and also use the mass ratio factors if you have a two-phase. If you have a hexagonal phase, you may want to use the Miller-Blavi index. That's a 4-digit index system, and we provide you tools here. You can change your Miller index to Miller-Blavi index here, both for the refraction, the zoom axis here, and this is for both way. If you put the number here, you do this button, and you get the 3 digits index and the zoom axis. If you put the number here and you do this, you get the Miller-Blavi system. I made a few adjustments for the patterns. First, reduce the size of experimental one, redo the calibration, and also change the grain size to 50 nanometer and 20 nanometer here. Redo the calculation, readjust the index label positions. Now we get a pattern like this. You can save the display area to a file, either JPEG file or TIFF file. Before you save, please check ROI and TIFF. This is show where you want to print out. This is the maximum. If you reduce this a little bit, you can see the blue square. Inside the blue square will be saved to the image. For the TIFF PPI, point per inch, usually we used 300 or a little bit up. You may also save diffraction HKL and intensity list to a file. And here you can select which one in the files. by default is just HKL and arc intensity. You can also include the G and the D here, or the ring intensities. For your information, previous version PCED3 was published in Ultramicroscopy 2010, volume 110, page 297. The paper is also listed in the user manual. Hope the software will help you in your research work. For suggestions, questions, and license information, please contact us. Thank you for watching. Please check our other videos about Landyne software suite for electron diffraction simulation and crystallographic analysis.